All right, well, how are you doing? About the same as me? Okay, good. Good. Last week we were talking about oxidation. I thought I forgot an interesting detail that doesn't matter, but the reaction of chromium-6 based reagents to oxidize alcohols results in a color change. Chromium salts are usually like bright yellow, and then the reduced version of that, of a chromium salt, turns green. And so this has actually been used in a breathalyzer test before to detect alcohol in someone's breath. They blow through a device that has chromium in it. If it turns green, you're above the legal limit. So application in daily life, I guess. Let's see, anything you wanted to know more about biological oxidation? Not really. Okay.
Right here.
Yes, go ahead for it.
What do you want us to know about?
Oh, yeah. Everything. What do I want you to know? Basically what I drew here. One interesting thing about the reagent NADH that we're not totally there to talk about, probably won't be till 352, is the idea that if you look at the reagent before the reduction reaction, you've got a fully conjugated ring, right? Each of these carbons is sp2 hybridized, so is the nitrogen. They're involved in pi bonds. There's resonance structures where you could switch the position of the pi bonds. But that is broken when you add the hydride to NADH. Now this is no longer fully conjugated. You got 5 atoms that are involved in resonance with each other, but this is an sp3 carbon. And it's thought that this switch between what someday in 352 you will learn to call aromatic to non-aromatic is part of why this reduced form of NAD plus, called NADH, you can actually go backwards to. So it's a hydride acceptor because you've got a positive charge in the ring, but NADH can be a hydride donor. And in fact, I told you that NADH gets taken to the electron transport chain in mitochondria, where it donates the electrons from this bond and the proton to drive the formation of the proton gradient across mitochondria. Good. Can you write all that in an essay for the exam? No? Okay, don't worry about that. At most, recognize what oxidation and reduction are. I really can't think of a useful question. Which of the following is NADH? That sounds kind of dumb, so I probably won't do that. All right. You think I should do that?
Yeah.
Okay. Yes. All right. Speaking of conjugation, chapter 22 is all about resonance, conjugation, and dienes. So some of this is going to be a needed review. Which means you can sit back, relax, and then if you don't know what I'm talking about, start to feel uncomfortable, I guess. All right, so what's resonance? Never quite sure, right? Any ideas? Go ahead.
It's when, like, a molecule can come in multiple different forms when the double bond is shared between multiple different.
Okay, so at one level, resonance is multiple Lewis structures for the same molecule. And when that happens, we ask which one is right, and the answer is yes. Resonance structures can give us an idea of the reactivity of molecules. You said something about pi bonds. How do you know when resonance structures are possible? Yeah. Negative charges over multiple carbons, that is one example of resonance that you've seen before. Boy, you've seen it a couple times actually on various stressful situations in this class, right? Should we just keep going? Yeah, where is the negative charge held?
Except that's not possible.
Huh? What's not possible?
Sorry, I'm looking at it wrong.
Okay, that's okay. Right.
Right there.
By the way, I mean, if you get this wrong on the final, I wash my hands and shake off my clothes before you. It will be entirely your responsibility. Okay? All right. So you've seen, where can the negative charge be shared? So one concept with resonance is delocalization, spreading out of electrons or charge. Okay, where else? How do you know when resonance is possible? Yeah.
You look for atoms that are next to each other that have p orbitals.
Okay, yeah, pattern in resonance is atoms next to each other with p orbitals. Good. What about this? Are we in a resonance situation with this molecule? This molecule is called an allene. I've drawn its geometry in a specific way. I've got p orbitals here and here, right? And on here. Is carbon 1 conjugated to carbon 3? Some of you are shaking your heads no. How on earth do you know? Prove it. It's okay if you're just guessing. Go ahead.
Because like the bonds are staying where they're at, like the electrons don't have to move over.
Okay, the bonds are staying where they're at. You don't have a charge that indicates, right. I suppose one could argue, and this is, it's a decent argument, that you can draw a resonance structure for a simple alkene, right? I could draw this one. Probably in general chemistry they told you to feel uncomfortable with that because of unnecessary charge separation. Nevertheless, hopefully you've learned in organic chemistry that sometimes these charge-separated resonance structures can tell you a little bit about the reactivity of an organic molecule. Aldehydes are electron poor at the carbonyl carbon. Anyway, that's sort of an aside. You can sometimes tell whether resonance structures are good or bad by looking at whether the most electronegative elements have a full octet of electrons. And so even though this resonance structure involves charge separation, it's a decent one because it indicates something that's real you can observe about aldehydes, which is they're electron poor at the carbonyl carbon. So the fact that there's no charge here, I mean, if I wanted to, I could put a negative charge here, a positive charge there, and so on. But I guess what I mean is, what do I mean? I asked the question, are carbons 1 and 3 conjugated to each other? Go ahead.
I'd say no, because the p orbital on 1 is like in the plane of the page, but on 3 it's running in and out of the page.
Okay, good. How do you know that?
It's where the hydrogens are at.
All right, where the hydrogens are at. So if you start with geometry, this carbon is surrounded by 3 things. It's got to be sp2 hybridized, trigonal planar. The plane is indicated by these 3 bonds. You've got one carbon-carbon bond in the plane of the page. You've got a carbon-hydrogen bond coming out at you, and another going back into the page. So we're sort of looking on it side on, and you're right, the p orbital that is involved in the pi bond on the allene is right here. And you mentioned that on carbon 3, you can tell carbon 3 is also sp2 hybridized, but in this case, the carbon-hydrogen bonds and the carbon-carbon bond are all trigonal planar, but in the plane of the page as it's drawn here, which means that the p orbital on carbon 3 would be coming out towards you with a node in the page and then going back into the page with a switch in wave function sign. So, so what about that? Why does that mean they're not conjugated to each other? What's a requirement of conjugation? Go ahead.
Because the nodes have to be lined up to like share electron density. So
Okay, what has to be lined up?
like the matching wave function design.
Okay. Right. Orbitals that are orthogonal to each other, orthogonal orbitals don't interact. That word orthogonal is confusing. It has a specific mathematic definition that is consistent with our definition, which will be orbitals that are 90 degrees apart from each other. Ortho means right, I think. So orbitals that are at a right angle with respect to each other don't interact. It's sort of a dot product thing. I think if you ever remember in vector math, or maybe it's cross product, I can't remember which, but it's one of those two where if vectors are perpendicular to each other, their cosine of theta equals 0 or something like that. Anyway, right, so what about carbon 2 here? It's sp hybridized, it's linear. It's got one p orbital here. That one can line up with the p orbital on carbon 1. That accounts for one of these pi bonds, right? And then what else? There's another one here and then back into the page where we can get another pi bond. All right, so because the p orbital on carbon 1 is perpendicular to the p orbital on carbon 3, those two don't interact. Carbon in the middle interacts with both of them, one on the one side, one on the other side. It's got two p orbitals it can do this with, but carbons 1 and 3 are not part of the same system of pi orbitals. So let's see what we're getting so far in terms of requirements for conjugation. We've got, you need, let's see, p orbitals lined up. If conjugation is going to involve p orbitals, what is the hybridization of carbons that can be involved in conjugation? sp2 or perhaps sp, right? I suppose that in this molecule, if you could make it, this carbon is conjugated with each of these other two. Because even though the even though the alkyne involves sp hybridization, some of the p orbitals are going to be able to line up with that adjacent carbon. Okay, so your carbons need to be sp or sp2 hybridized. You need to have p orbitals lined up with each other. Let's see, what else? Are these two pi bonds conjugated with each other? Yes, no? We haven't really defined what conjugation means, so yeah, go ahead.
I think no, because they're separated by a bond.
They're separated by a bond. Okay. Let's see. Let's look down. We're looking down at this molecule. We'll put all the carbon, hydrogen, and carbon-carbon sigma bonds in the plane of the page. I don't know why we've got this methyl group here, but we'll keep it now. sp2 hybridized carbon. I'm going to draw p orbitals there, and this would be sort of what the pi bond would look like. On the adjacent carbon, I also have, on the adjacent two carbons for the other double bond, I also have two p orbitals that can line up with each other to form the pi bond. Now, does it look like those p orbitals are all aligned with each other? Yes. Yes, yes. Sorry. I need to come up with better questions. This is a situation where carbons 1, 2, 3, and 4 are part of the same conjugated pi system. And if you remember some of the stuff that we did at the very beginning of the semester, you can mix these 4 p orbitals together to get 4 pi molecular orbitals out, right? Just as we've done before, where you mix 2 orbitals together to get a bonding combination and an anti-bonding combination, you can mix 3 or more orbitals together to get 3 or more pi-type molecular orbitals. This is one of them, though we could draw some of the other ones too. For example, let's see, let's just switch. Oops, that was not what we wanted to do. Nope, still no. Gotta target that eraser. There we go. Oh no, I did it the wrong way again. So the combination where the first 2 are in phase or with the same wave function sign with each other, and then the next 2 are, we'd have a node here. We'd have 0 nodes here, 1 node there, and we could go on and draw the rest of them. We won't necessarily do that now, we'll do that in a little bit. Okay, with that in mind, let me give you a slightly different situation. How about carbons 1 and 2 and 4 and 5? Are they conjugated with each other? No. Okay, they are not. Why not? You got a sp3 hybridized carbon in between the two, one that does not have a p orbital on it. And therefore, though there is a pi bond on carbons 1 and 2 and another on carbons 4 and 5, because they're not adjacent to each other, there's no opportunity for them to mix with each other. So not only do you have to have p orbitals lined up, but they need to be on adjacent atoms. When I was in this class 22 years ago or something like that, Dr. Savage described conjugation as, quote, a contiguous, that's a nice word, array of p orbitals. Contiguous meaning they're on adjacent atoms. Array meaning a line, and p orbitals meaning p orbitals. And I guess we should add to that are parallel to each other, not perpendicular. Okay? And you're going to see that conjugation is really present anytime we can draw a resonance structure. So going back to one of these horrific examples from your previous experiences, where is my contiguous array of p orbitals that can line up with each other?
Right there.
Right there. Okay, help me out. Where? Ooh, where? You want the laser pointer? Don't hit my eyes.
Careful.
Okay, so every other, well, let's see. It's on my forehead now, isn't it? So each of these atoms is sp2 hybridized. Each of them has a p orbital on them that can line up. I suppose I could draw maybe the lowest energy pi molecular orbital that you might get from here simply by coloring in all of these the same wave function sign. Okay? That is a highly conjugated system, right? Thanks. You're giving up. Take it, Kronk. Feel the power. Oh yeah, I can feel it. Yeah. Let's see. All right, let's talk. Any questions you want to ask about what conjugation is? Yes.
I know that in this resonance structure should be every other carbon atom that would hold a negative charge. Is there more molecular sort of reasoning behind that?
You remember that the answer to this was based on the idea that when you draw resonance structures and you have a negative charge, or a positive charge for that matter, the charge is held on alternating atoms. Now, that is an important part. We get that from the fact that the smallest incremental change from one resonance structure to another for lone pairs adjacent to a pi bond is the lone pair two-step, which is you make a new pi bond here between the atom that had the lone pair and the atom to which it is adjacent. But if you stop there, you'd make this one a Texas carbon, so you have to break that pi bond and move it onto the adjacent atom. So yeah, you would conclude that the negative charge could be on this oxygen and on this atom, and you could go and generate multiple resonance structures that way. That's an illustration of the simplest resonance structure we looked at earlier this semester, where to convert one into another, you just use arrows like that. As we get back into the pi orbitals, you'll see that when we have an odd number of atoms involved in our conjugated system, the highest energy, either the HOMO or the LUMO, is going to be on alternating atoms. I think if you remember, we looked at what the pi orbitals were like for this allyl anion, and I'm just going to draw them as though we were looking down on the p orbitals from above. You've got three of them together with the same wave function sign, or you have two nodes where you switch wave function sign in the middle, and then the middle orbital is where you switch wave function sign at carbon 2. So that's really where this alternating issue comes from. For the allyl anion, if you remember from our earlier stuff, earlier study guides, there's 4 electrons involved in the pi system, so the highest energy electrons are held here. So yeah, if you're in a conjugated system that has an odd number of atoms, either your HOMO or your LUMO is going to be on every other atom. I say HOMO or LUMO because we could draw the allyl cation. We'd have exactly the same pi molecular orbitals, only the one here would be empty, and your LUMO would be on every other atom, and that's exactly where resonance tells you the positive charge is. All right, yeah.
So with the conjugation, would a benzene ring, like we see in the equation, would that always be conjugated with itself?
Sorry, will a benzene ring always what?
Be conjugated with itself?
Will a benzene ring always be conjugated with itself? If they're fused together like this, yeah. Yeah. Okay. What else you want to know? Do you want a preview of benzene? No, you really don't.
Yes, we do.
Yes, you do. Why not? It's maybe. So I want to just take a second. It's not a huge deal, but it's interesting to ask what happens for a conjugated system when you turn it into a ring. And this will be a preview of a topic that you'll talk about in 352. Let's just draw the lowest energy, the sort of pi1 lowest energy filled orbital for this molecule, which is 135 hexatriene. That would be where you have a p orbital on each of the carbons. We're looking down on this molecule from overhead. These are not s orbitals. You got it right. Like we're looking down on the p orbital. I'm not drawing for you the other lobe on the other side. Well, now I am, because I'm worried that you're going to misunderstand me. So yeah, we're looking that all of these carbon bonds are in the plane of the page. We're looking down from above on the lowest energy filled pi orbital, no nodes, right? Now, constructing an analogous orbital for benzene would simply involve connecting atoms 1 and 6. So we could literally wrap the orbital we generated on the left around the ring on the right, and we would get this one. That's a thoroughly boring conclusion, right? But do you think, well, again, leading question, do you think these two orbitals for benzene versus 135 hexatriene, do you think they're the same in energy? No, probably not, because otherwise why would I be asking about it? But how could that be true? Like they're both just 6 p orbitals all together. Yeah?
Because the closeness of the benzene helps it to conjugate more.
Okay, the closeness, the cyclization of the benzene ring probably holds things together. These are single bonds here between carbons 2 and 3 and between whatever, 4 and 5. Yeah, we can't count this morning. So you can rotate around those. Doing so would tend to break conjugation, so you'd expect there to be a bit of a barrier to rotation. Nevertheless, you totally can. For 1,3 dienes that we've maybe mentioned above, you can rotate around that carbon-carbon bond to get 2 different conformations. So yeah, you might expect that on average, because this ring is flat, it automatically constrains the p orbitals to be lined up with each other all the time. And that's not true for 135 hexatriene, right? So that's good. We can rotate around single bonds in 1,3 hexatriene, but certainly not in benzene. What else do you notice? Yeah?
There's 3 single bonds in the benzene ring.
3 single bonds in the benzene ring versus 2. Okay. Right, so we have to make sure we're comparing apples to apples in, by the way, I hate that game. Oh. I don't know, maybe I just played it too many times with one of Amber's cousins that always wanted to play it, but just. It's even worse with children, by the way, because children, there's no rationale for why anybody chooses one thing versus another in apples to apples. All right, sorry. No, you're right that there's one more sigma bond. Let me give you a sense for what the resonance consequences of benzene are versus the 135 hexatriene. I can draw a neutral resonance structure where instead of the double bonds being between 1 and 2, 3 and 4, and 5 and 6, I now have them between 2 and 3, 4 and 5, and 1 and 6. Okay, in contrast, I suppose I could draw a resonance structure for 135 hexatriene that would look something like this. But that's not necessarily as good as the benzene resonance structure, right? That's telling you something. If I started from this resonance structure and linked carbons 1 and 6, then I would have two adjacent atoms that are now conjugated to each other directly adjacent to each other and could make a new pi bond between the two of them. One other way and so that's part of recognizing what's different. Without getting too much into the molecular orbital theory, you can sometimes judge how stable an orbital is, especially a conjugated orbital, by how many times adjacent p orbitals are next to each other with the same wave function sign. This is one way that you can rank pi molecular orbitals. As an example, if you didn't already know about nodes, you could look at these 3 pi orbitals from the allyl anion, and we could count each time that a p orbital is adjacent to another p orbital with the same wave function sign as being a bonding interaction. So you've got two sort of bonding situations here because the p orbitals on 1 and 2 and 3 are matching in the same wave function sign. Whereas up top, you've got an anti-bonding interaction because you have two p orbitals adjacent to each other with opposite wave function sign. Here, the one in the middle, there is none of the p orbitals in this drawing are next to other p orbitals, so this is simply a non-bonding orbital. Which makes sense because we've talked about this orbital representing the lone pair that's on carbon 1 and 3, but never on carbon 2. So this is, I'm not going to ask you to do this, but this is one way you can rank pi molecular orbitals. How many times do you have wave function on two adjacent atoms that has the same sign? So let's sort of count up the number of bonding type interactions we have in 1,3,5 hexatriene. Got one there, one here, and one there. That's 5, right? How about in benzene? 6. Cyclizing that contiguous array of p orbitals allows you to pick up one miraculous, that's sort of supposed to be a star new bonding interaction. So you get one extra cyclization here of the conjugated system gets you one bonus bonding interaction. And it turns out that benzene's stability relative to 1,3,5 hexatriene is as though it had half of one extra pi bond. And benzene's stability relative to 3 isolated pi bonds is like benzene had a full additional pi bond. So anyway, I don't know why we got into that other than to say that, stay tuned, conjugated molecules that have this capability, that have the ability for a bonus bonding interaction can be especially stable, and that is a concept that we call aromaticity, or we would say the benzene ring is aromatic. And that was a name originally because some of these molecules tended to be volatile and have characteristic smells, but we use that word now, aromatic, not to describe the smell, but to describe the special stability that you get by taking a conjugated system and making a ring out of it. Just as another preview, it doesn't always work. You got to have the right number of electrons, but we're going to save that for your future. We'll just delay that until then, and to just sort of, to scare you, benzene is especially stable. 1,3-cyclobutadiene, very, very, very bad. Very unstable, even, and we sometimes call it anti-aromatic. And that doesn't have anything to do with its ring strain. So we'll just let that one float out there, and you can be excited to learn about it in a few months. Some of you aren't going to sleep at night now worrying about that. You're welcome. All right. Other questions about conjugation? Okay. Let's take a minute and talk about conjugation and vision. And I'm not talking about Wanda Maximoff's love interest. So let's see. Maybe this is best illustrated with Spartan. I'm going to draw that's not the right one, 1,3-butadiene. And then we're going to, look at, the molecular orbitals. And let's just look at the gap between HOMO and LUMO. Now, Spartan has this interesting feature where it will give us the energy of that orbital in electron volts. I hate electron volts as a unit. I don't know what it means. I prefer kilocalories per mole. Nevertheless, there we go. Minus 6.1 electron volts for the HOMO. Somebody write that down because we're going to do some subtraction. For the LUMO, minus 0.71 electron volts. Okay? That's for 1,3-butadiene. Gap between HOMO and LUMO is like 5 point whatever electron volts. Somebody do the math. I'm not doing the math. What's the difference between these two? 6.1 minus 0.71. 5.3. Ooh, let's limit ourselves to two significant figures, shall we? Let's just make our lives easier. By the way, we have a bathroom scale, which I hate, but it reports weight in like far too many significant figures. The plus or minus on that thing is a couple of pounds, but in the meantime, it's reporting 0.1, 0.2, and it's very irritating. Shall we tell you about the time that, the Christmas that my mother got us a bathroom scale? Wasn't meant to communicate anything. We actually wanted one, but it was funny. All right, so here's 1,3,5-hexatriene. Let's look at the molecular orbitals. Again, we're going to look at HOMO versus LUMO. Write down that minus 5.6. And then the LUMO we'll call minus 1.3. All right. Minus 5.6 minus 4.3. So we said that for, at least according to Spartan, for 1,3-butadiene, the difference in energy between HOMO and LUMO was 5.4 kilocalories per mole. No danged electron volts. And whether it's positive or negative would be depending on whether or not we were going one direction versus the other. And then let's see, for the 1,3,5-hexatriene, what was it? 4.3. All right, 4.3. That's fine. Okay. One of the things we notice is as you bring more atoms into conjugation, the gap in energy between HOMO and LUMO gets smaller. Okay? That's a general feature of organic molecules. The more conjugation you have, the more pi orbitals you pack into that space, the smaller the difference in energy is between HOMO and LUMO. Now, a 1,3-butadiene absorbs light through a HOMO to LUMO transition in the ultraviolet. So if you had a sample of 1,3-butadiene, you wouldn't see any color. But as we start to increase the number of bonds that are in conjugation with each other, the HOMO-LUMO gap decreases, and you can start to get molecules that absorb visible light. And so most of the dye molecules that are involved in coloring clothing and other things are highly conjugated molecules. So let's see. Oh yeah, by the way, that barbecue mac and cheese pie was excellent. Made that on Pie Day. It was fantastic. Let's just Google dye molecules and see if we can get a few structures from Wikipedia or somewhere where you can see how highly conjugated they are. That looks interesting. Too many metals. We don't like metals. Okay, so this molecule is indigo dye. You can see that it's highly conjugated in the sense that we've got benzene ring. How about these three atoms? Are they sp2 hybridized? Yes, no. How about, is this one sp2 hybridized? How about this one? This one? Yes! That's another interesting feature. Lone pairs adjacent to pi bonds, you can delocalize the lone pair if that atom is sp2 hybridized. So yes, nitrogens adjacent to pi bonds are going to be sp2 hybridized so that a lone pair can be in a p orbital so that it can line up with the others and participate in resonance. All right, so this would be a system where you have, let's see, 6 plus 3 is 9, 18 atoms in a contiguous conjugated array, and it's blue. Let's see what else. No, not that. Let's go with, no, all right, fine. Mauveine. So this is an interesting story. There's a dye called Mauvine, or Mauvine, I'm not sure. This was developed by a chemist named William Perkin in 1856. He was a teenager, and he had a lab in his basement, and he tried to do a reaction, and it didn't go well. And he was trying to clean out his round-bottom flask, in which was this chunky black solid at the bottom of the flask, and that usually means your reaction failed. And as he was trying to clean it out with a particular solvent, the solvent dissolved some of the chunky black solid, and it was bright purple. And instead of saying, oh, that's kind of interesting, and then throwing it away, his mind went to work and said, whoa, purple is hard to come by. And in fact, you can read in the New Testament, Lydia was a seller of purple, which meant that she either bought or captured sea slugs and ground them up and got the purple out of the sea slugs, and then that kind of stuff was used to dye clothing. It was very expensive. Perkin had just made purple dye very cheaply, and it made him basically a gazillionaire. He was able to retire at the age of 36. And was independently wealthy. Anyway, these are some of the molecules that he formed on accident. Talk about serendipity. But you can see they're all highly conjugated, even more than the indigo dye. You've got a lot of sp2 hybridized carbons adjacent to each other. And it turns out that Mauvine is not actually one molecule because, of course, he didn't know what he was doing when he was making these. It's a mixture of molecules. Go ahead.
So is there a certain point where like you'd start reflecting UV light or like X-ray light?
Let's see. Is there a point where it would start reflecting UV light? Well, we're talking about molecules are colorful when they absorb some visible light and reflect other visible light. So presumably, Mauvine absorbs in the red and green, but not so much in the blue end of the spectrum. X-rays are energetic enough that they actually do other things to molecules. Both X-rays and ultraviolet rays can actually excite molecules and cause them to do things they wouldn't normally do. At some point, maybe we'll tell you, at some point in 352, we'll tell you why you get sunburned, which has to do with UV light. I would say that X-rays are energetic enough that they're most likely to damage molecules rather than be reflected by them, I guess. Oh, how fun. Professor Charles Rees, wearing a bow tie, died with an original sample of Movine. That's probably a very expensive bow tie. Holding a Royal Society of Chemistry journal named after Perkin. Between 1859 and 1861, mauve became a fashion must-have. Anyway, there's another interesting story in chemical history. The development of dye molecules actually inspired and paralleled the development of chemotherapeutic drugs. That's a whole other story that we may want to tell you some other time. Now, what does this have to do with anything other than you like to wear colorful clothing? And the answer is it's also how you see. So I'm going to show you 11-cis-retinal, which is a molecule that's involved in vision in your eyes. Okay, so this molecule 11, this is all trans retinal. Let's see, they've got, are they going to show us the cis one? No, maybe? That's it. Somebody needs to tell Wikipedia to stop generating. Oh, I guess it's okay. I was going to complain about the graininess of this free figure that's freely available to everyone, but all right. So 11-cis-retinal is a highly conjugated molecule. Do we have to memorize the structure of that? Please do not. It's got a cis double bond here at carbon 11, and in contrast, you've got this trans isomer here. What do you know about cis versus trans? Which is more stable, all the things being equal? Trans because of sterics, right? You could draw, there's a carbon-hydrogen bond pointing here directly at this carbon-carbon bond. Steric problems there that you don't have in the trans isomer. So 11-cis-retinal is loaded into the protein called opsin. That protein does not look like this. That's somebody just drawing a cartoon and telling you it is a protein. Get ready for biochemistry, folks, because that's how they draw proteins in biochem, even though they don't look like that. So the retinal gets loaded in there. It absorbs UV light, or it absorbs visible light because it's highly conjugated. That means the HOMO-LUMO gap is in the range of visible light. Promoting an electron from HOMO to LUMO can weaken a bond, right? And that allows for this cis isomer to relax and isomerize to the trans isomer, but that results in a change of shape to the molecule, which is felt by the protein. Let's show you, oh no, there we go. Here is the, rhodopsin is a membrane, transmembrane protein. You've got the retinal inside. When it absorbs light, it changes its shape. That gets communicated to this intracellular stuff, which causes a cascade, a nerve signal, and then you see. So HOMO-LUMO has been going on in your eyes since you were born, and is one of the reasons you can see stuff now. All right, see you next time.